All right, so let's get started. We finished up chapter 8 last week. Chapter 8 was what? Solution chemistry. So it was chemical reactions happening in water. So we're going to continue on with that idea of things dissolving in water. Just within this chapter, chapter 9, we'll be specifically thinking about acids and bases. And so we have acids and bases within our bodies. They are the reason why our bodies work the way they do. So here's what we'll be talking about in chapter 9. And just to kind of recap, this chapter, chapter 9, is covered on midterm 3. I do plan on finishing up this chapter on Thursday. There's only about 50 slides, and a lot of it's based upon concepts we actually already know. And then, midterm 3 will cover chapters 7 through 9, so that includes gases, intermolecular forces, and solution chemistry. That was chapter 8, and acids and bases, chapter 9. And then looking ahead for the final, we will still cover 3 new chapters, so chapters 10 through 12, but they're fairly short. All right, so they're fairly short. I think they're like 40 or like 20 slides each. So I kind of just pick and choose the different topics within those last 3 chapters. But then within the final, everything is cumulative. So we cover chapters 1 through 12. So, you know, the material on midterms 1 and 3 will be covered on the final, plus chapters, 10 through 12. So do anticipate about a fourth of the final is new material, but the other 2/3 is older material. All right? Any questions about that? Yeah. Okay, so the question was, will there be, what happened? Did I get kicked off? I got kicked off. So the question was, will I make available a practice final, right? Because I've done that for every midterm. I will post new questions for chapters 10 through 12. For the final, since you have access to midterms 1 through 3, all of those practice exams, I won't be posting a comprehensive final practice exam for you. I think I'm not allowed to post practice finals, but I can instead just post, I can post a list of questions, example questions. I'm not going to call it a practice final. It'll just be a list of questions that you can do. So do anticipate that. There'll be some questions, but it's not going to be as comprehensive as the previous midterms, but do use those materials from the previous midterms as study material. All right. Okay, so sorry, Zoomers, the internet doesn't work in this room, so I'm hotspotting my phone. All right, so let's get started. Any other questions about midterm 3? So you saw information, you see all of the study materials for midterm 3. It is next Thursday. Yes, question. So on the question is there a list of topics to study for the midterm? So for it's exactly the same topics for all the midterms as well. So if you look at the learning objectives for every chapter, particularly the ones that I highlight, those are the topics that are the important ones. Yes? Is it still 25 questions? The final? No, it is not. Since it is a longer exam, it will be more questions. I don't want to say the exact number, but midterm 3 is 25 questions. Sorry, was that your question? No. The final, okay. But midterm 3 is 25 questions. I do anticipate the midterm probably being closer to 40. I don't want to say that number, but I'm going to say 40. Other questions? Yes. Yes. Oh, yes, it is longer. It's the university time window. I think it's an hour and 45 minutes. Is that right? Yeah, so whatever I will anticipate that the length I give you for each question will match, right? But just will be scaled to a longer exam because it's an hour and 45 minutes. So it's not going to be longer than what the university gives me in terms of time. Okay, good? All right. Okay, good thing we're looking ahead to the final. All right, so chapter 9, acids and bases. Let's get started. So keep in your head the idea of what things look like when they're dissolved in water, because all of those concepts still apply here. We just so happen to be talking about acids and bases. Okay, so what are acids and bases? You know, the word acid has a very bad connotation when it comes to like chemophobia, whatever. All right, when we say, ooh, that's bad, that's an acid. But the thing is, the definition of an acid, once we get to the end of the chapter and talk about pH, an acid is anything that has a pH lower than 7. All right, so lower than 7. So anywhere between 6.9999 and down is essentially considered acidic. Actually, tap water, regular rainwater, is actually acidic because there's dissolved CO2 within water and it makes it slightly acidic. So I have an issue with people who have chemophobia and they think, ooh, acid, that's bad. A lot of the things we eat are acidic, slightly acidic. I mean, in its terms of magnitude, right? If something's very, very, very acidic, yes, it can hurt you. But within the realm of nature, things don't get too acidic. And so the term acid or base, in this case, we shouldn't be looking at it through like the lens of chemophobia. It's just a term that relates to the concentration of H+, which we consider an acid within a solution. That's really all it means. So we'll dive into the details of that there. All right, so just historically, when thinking about acids and bases, when, really the beginnings of chemistry, they categorize acids and bases based upon just like the properties that they observed. And unfortunately, how they observed chemicals back then is they tasted them. So obviously we don't do that now. All right, but historically, acids were identified by things that were sour, while bases, things that were basic, were things that tasted bitter. All right, so I don't want you tasting chemicals, but I will point out that most foods that we eat are acidic. Acidic things are tasty to us, to humans, right? That's why like soda is so tasty. It has a lot of dissolved CO2 in it, makes it bubbly, but it's also really acidic. And that's why dentists say, don't drink too much soda because the acid will dissolve your teeth. But, in moderation, that stuff's really tasty. There's not many foods out there that are basic. And I think the question, was it in this class or my other class? Said something about bases, and did I go on a tangent about Tom Brady in this class? No, I didn't? Okay, all right. So here's my tangent about Tom Brady. I was reading a book, and they were talking about Tom Brady, right? He retired from the NFL, but then he said, wait, whoops, I take that back. And now he's not retired from the NFL. Yeah. He is on a alkaline diet. So what that means, an alkaline diet, when we think about like the alkaline metals, those are metals. Typically those metals are associated with bases, all right? So his diet is a slightly basic diet. Like Gwyneth Paltrow, she touts this special alkaline water. It's just water that's slightly basic, all right? There's nothing special about it because you know what our stomachs are? It's super acidic in there. So if we drink something that's slightly basic, it's just going to be neutralized by our stomach anyway. So you're paying just way too much for fancy water. All right. Tom Brady, he eats an alkaline diet. Really what he's doing is robbing himself of delicious things like tomatoes, lemon, like anything. Really all fruits are acidic, and that's why they're tasty to us. He's just robbing himself of that. I don't know. He's a great football player. Maybe it is the alkaline diet, but I doubt it. Okay, so those are my feelings about acids and bases. And so really what it means is just where are you on the pH scale? Are you more than pH 7, basic, or are you less than pH 7, acidic? All right, so yeah, don't taste chemicals. All right, so going into the details of what differentiates an acid and a base, we're going to talk about two different definitions here. The first one is kind of more based upon observations and really the simplest way to define acids and bases, but it's not the best way. So the first definition is the Arrhenius definition, so it's named after the guy who came up with it, savant Arrhenius. And so an acid, when we think about acids, always associate an acid with an H, specific like a hydrogen, specifically with an H plus, right? The idea and the existence of an H plus cation typically indicates that something is a base, an acid. And in this case, H plus, that's the cation. So a hydrogen cation here. All right, so an Arrhenius acid is simply a substance. Oh my gosh, is my pen out of batteries? I'm not prepared right now. All right, so no, it's not. A substance that is an Arrhenius acid, so this guy, his acid, is just any substance that when you put it in water, it increases or it produces H plus cation. So again, recognize and associate the existence of H plus with acid. So something that has a lot of hydrogen cation is an acid. Something that doesn't have a lot of H plus is a substance that we would consider basic. So lots of H plus means very acidic in this case. So you can see this is just a generic acid, so I just put HA. So A could be anything, any a negative one charged anion. This could be a chloride, it could be a bromide, it could be anything. It's just something that has a H plus cation attached to it. All right, so on the other hand, acid means lots of H plus. An Arrhenius base is just the opposite. There's two ways to think about it. You could either think, hey, a base does not have a lot of H plus. If you put a base into water, what it will do is lower the H plus concentration, thus making the solution basic. Another way to think about it is a base is something that produces OH minus anion in water. So OH is hydroxide. It's one of the polyatomics that you should have memorized back, I don't know, chapter on midterm 1. So hydroxide, that anion, OH minus, is kind of the counterpart to our H plus cation. Because when you think about it, our OH anion here, so that's OH, right? When you mix an OH minus with an H plus, what do you get? An H and an OH becomes HOH, which is H2O. H2O is water. So basically the idea of an acid and a base, if you mix an acid and a base, H plus and OH minus, you get just neutral, pure water. So that's the big idea within there. And so that's why we kind of think of acids and bases as opposites of one another, because when you mix them with an H plus and OH, they cancel each other out and they give the product that they make is this neutral water. So that's the whole idea within there. And so just a little bit of detail here. So here's an example of a base, an Arrhenius base where we have sodium hydroxide. This is a base. This is ionic. There's a cation and an anion. So when we dissolve that in water, we have sodium plus, which isn't involved in the acid-base definition, but what is the existence of, hey, we've increased the OH minus concentration, so this is a base. And you can kind of think, in other words, if we increase OH concentration, what we also do is decrease H plus concentration. So there's two ways of thinking about that there. There are other bases, not just sodium hydroxide. It's really any of the group 1A or 2A metals that have a hydroxide attached to it. So the great thing about bases, especially these strong bases, is that the hint to identifying it is that there is an OH anion attached to it in some capacity. And with acids, the identifying factor here is that there's an H plus cation associated with that chemical formula. So that's how you identify it. All right, so how Arrhenius came up with this theory, it's the simplest theory. How he came up with this idea was through observations. And I'm only pointing this out because when we go to the next definition, it's a little bit more sophisticated. In this Arrhenius definition, what he just did was took different substances and reacted it with carbonate. Carbonate is CO3 2-, all right? So he reacted different substances with carbonate. And he basically looked for the thing that we added to carbonate are bubbles produced. That's what he was looking for. Because if you react an acid with carbonate, CO3 2-, if you do the double displacement like we have before, the product is H2CO3, or carbonic acid. And we'll talk about naming acids a little bit later. So yeah, when you mix an acid and carbonate, you get H2CO3. The subtlety here is that this compound, carbonic acid, is really unstable. So what it does is immediately decompose into CO2 and water. So basically, his observation, what he did is he took random unknown substances, added it to carbonate. If he saw bubbles, he called that substance an acid because that means it has H+. Does that make sense? So that means if you add an unknown substance and it doesn't make bubbles, that means it's not an acid. So all of his ideas of his theory are based upon observations. And so another reaction that can happen with acids, if he was trying to identify of something as an acid or a base, was if it reacted with zinc solid. So some acids will also, if you drop in a piece of zinc solid, more bubbles will be formed. All right, so all of these based upon observations. If he did in fact throw in an acid into carbonate or zinc and saw bubbles, he called that thing an acid. That's basically what he did. On the other hand, so that's how he kind of identified unknown acids, whether to identify something as a base or not, same kind of idea, but he chose a different substance. So most hydroxides will react with metals to produce solids. So what he did is he just took random substances, random unknown substances, and asked himself, mixed in some type of metal, like such as magnesium 2+ cation. So he added these unknown substances to magnesium 2+, and if a solid was formed, he knew that that solid was magnesium hydroxide. All right, and so if magnesium hydroxide was formed, it's just a white solid. So if you saw a solid being formed, that means that that unknown substance has hydroxide in, in its chemical formula. So that's how he identified bases in that case. All of these based upon observations. So really, it says nothing about the chemical structure of the substance at all. With the Arrhenius definition. It was just the idea of, hey, acids produce H+ in solution, bases produce OH- in solution. That's basically it. All right, so on the other hand, our second definition of acids and bases is a little bit more specific and sophisticated and more based upon the structure of the substance itself. Right, so it's a lot more specific. It's not just based upon observations like Arrhenius did. So this is the Bronsted-Lowry acid and base definition. So that O has like an X through it, but sometimes I'm really lazy, and when I type it out, I don't put the cross, because I have to go to like Word and symbols and find the O with the slash in it, and that's really hard. But his name, Bronsted, does have that slash in it. Does anyone know what that's called, that symbol? No? Okay, all right. I know if there's two dots, it's an umlaut. Okay, that's all I know. All right, so Bronsted-Lowry, how is this definition different? So the note here that we're still talking about acids and bases, but just a little bit differently. So I'll just state the definitions here. I guess the first thing I should say is in the previous definition, we talked about H+ cation. Increasing or decreasing with acids and bases. Let's think about what an H+ cation is. A hydrogen atom, what are the subatomic particles in a hydrogen atom? How many protons are in a hydrogen atom? Where do we get that information? The periodic table. So a hydrogen atom has how many protons? 1. How many neutrons does it have? One. So what's the mass, the atomic mass of a hydrogen? Isn't it like 1? It's just 1. So there's actually 0 neutrons on a typical hydrogen atom. So when a hydrogen is neutral, how many electrons are there? 1. Okay. But now we're talking about a hydrogen cation. So that means a cation, we lose that electron. So if we think about all the subatomic particles in a hydrogen cation, it's just a proton. That's it. So when I say hydrogen cation or proton, they mean the exact same thing. Do we see that? Because a hydrogen cation, based upon its subatomic particles, it is just a proton when it loses that 1 electron, when it's a cation. So that's the first thing here, because oftentimes the Bronsted-Lowry acid and base definition talks about substances gaining or losing protons. So when I say gaining or losing protons, I really just mean gaining or losing a H plus cation in this case. So a Bronsted-Lowry acid. So note here, it's the same acid as the example I did before. We just have a generic HA. A Bronsted-Lowry acid is a compound where that proton can be removed and donated to a different substance. So let's think about this. Let's think about this picture. So this HA, that's an acid. We know it's an acid, but why it's a Bronsted-Lowry acid is because that hydrogen, let's track where it goes. So on the reactant side, that hydrogen's right here. Okay, but what happens is that this water that's also in solution, because this, you put acids in water, this is all solution chemistry, that water picks up that hydrogen, because then on the product side, see what water becomes. It becomes H3 plus. So see how water gained that proton or that H plus cation, but the question is, where did it come from? Where did that H plus come from? It was donated to water by the acid. So this is just a different way to think about the idea of an acid and a base. So when water picks up that proton from the acid, we don't forget about the anion, the A anion that's there. It's still there as well. So if you kind of look at both sides of the equation, everything's charge balanced, because when we look at this, it's like plus and minus, it cancels out, and all of the right number of atoms are there as well. If we just look at this, the hydrogen is moving from the acid, it's being donated from the acid to water in this case. And I'll show you a particulate diagram that kind of clearly shows the actual atoms and how they're moving. So the Bronsted-Lowry acid definition says that acids are proton donors. They give protons to other things, and a proton is just an H plus, right? So on the other side, remember, like acids and bases, it's like the yin and yang of they're like opposites from one another. Okay. What was I saying? Okay, zoom. They're opposites of one another. So if an acid, a Bronsted-Lowry acid, is a proton donor, that means that a base would be a proton acceptor. Yeah, so if you kind of think ahead or, use your intuition here, but I'll show you it anyway. Yeah, here's our definition here. A Bronsted-Lowry base is a compound that can accept a proton. And so an example here of a base, this is an example of a weak base, which we'll go into more detail about a little bit later, but ammonia, NH3, is a weak base. And so what's happening here is that ammonia, oh, you can't hear me. Okay, where's my other AirPod? Oh, why am I muted? Thank you, guys. Okay, is that better? I'm sorry. I'm hot spotting from my phone, so it's like really bad right now. All right, so what was I saying? Okay, so ammonia is a weak base. Bronsted-Lowry bases are proton acceptors. So what's happening here in this reaction is that ammonia is picking up a hydrogen, one of the hydrogens from water. So remember, water is like, you can think of it as like HOH. It's picking up one of the protons, and then on the other side, since ammonia is picking up a proton, it becomes NH4. So it gains a hydrogen, it also gains that positive charge, all right? And so thinking about the counter anion within water, OH is also left over as well. And so this is showing that ammonia can act like a proton acceptor in this case, making it a Bronsted-Lowry base. And this reaction actually that I've shown right here is kind of the proof that ammonia is a base. Because if you recall in the previous definitions of bases, or strong bases, I told you that like the giveaway of a base is when hydroxide is in the formula, right? But ammonia, if you look at ammonia, NH3, does that look like a base? Does that formula, does that have a hydroxide in it? No, it doesn't. So like a normal person would look at NH3 and be like, how is that a base? This is the reason why it's a base, because you actually have to react it with water. So when you react it with water, this reaction is actually a reversible reaction. Some of it goes forward, and what happens is that ammonia picks up an extra proton, but rips it off of water, leaving a hydroxide. So when you put ammonia in water, both of these sides of the reaction exist at the same time. So since there's an increased amount of OH minus in solution, it makes ammonia a base. And so that is just kind of like a weird example of one of our weak bases. They're a little bit harder to define, weak bases, than weak acids are. All right, so there is Bronsted-Lowry definition. And so here, I showed just a particulate view of the same thing that I was just saying. And so if there's one thing that you remember in these slides, is that a Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. And so this is what I mean. If we look at this example, so this is an acid and a base, or sorry, an acid. So we're putting NH3, so nitric acid, in solution. So there's that proton, H+. Nitrate is the counter anion here. So I'll just highlight where that hydrogen atom, or sorry, hydrogen cation is. It's right there on this formula. And so if we do this reaction in water, that proton on nitrate is just going to associate and be donated to the water molecule. Because when we look at this reaction on the product side, see how that water gained one of those H+ cations. But then in doing so, it was ripped off of nitrate in this case. So in this example, nitrate is the proton donor because it's donating its H+, and water is accepting it. So that makes water actually what in this example? So if here's the acid, nitric acid is our Bronsted-Lowry acid, it's donating the H+. And then water is accepting it. Water is accepting an H+, so doesn't that make that an H+ acceptor? It makes it a Bronsted-Lowry base, right? So in this example, the nitric acid is the source of H+. It's the acid or the H+ donor. Water is the H+ acceptor. It's actually a Bronsted-Lowry base in this example. That's really weird because you wouldn't think of water as a base. Water is neutral. But that's the really special thing about water. It can actually both act as an acid and a base. Yeah, that's what I have here. Water, if we think about the formula of water, I'm just going to call it HOH in this case, it can do one of two things. It can either, that first H I wrote, it can be donated to something else. All right, so water can act as an acid, right? If we subtract or donate an H+, it becomes OH minus. So that's it acting as an acid, or it can pick up an extra H+. And in doing so, it creates H3O plus in that case, and this substance actually exists. It's called hydronium ion. Really, it's the same thing. H3O plus is the same thing as H plus in solution. Sometimes book authors like to write H3O plus instead of H plus, but really they mean the same thing. Because when you put H plus in water, the two things, they combine with one another and make hydronium in that case. And so in this example, it's showing two different ways of water behaving, like I just said. So when we mix water with ammonia, ammonia is going to accept one of the protons off of water in that case. So here water is acting as the acid, the base, ammonia is acting as the base. And then in the second example, we have water acting as a base instead with an acid such as HCl. So HCl is donating the proton, water is accepting the proton, so water is acting as the base there. This is very peculiar, but as long as you get straight that with the Bronsted-Lowry definitions, acids donate protons and bases accept protons, then you will be able to identify any substance based upon the chemical formulas or chemical equations that are given here. All right, so those are Bronsted-Lowry stuff. Okay, where am I? All right, so I kind of mentioned it before, the idea that we have strong acids, strong bases, weak acid, weak bases. So I'll go into the details now here. So just straight off the bat, there are 6 strong acids you need to memorize, like right now. Right now, just memorize them. Okay, this will help you in the long run, because as long as you memorize these 6 strong acids, everything else that's an acid that's not one of the 6 is therefore a weak acid. See, so you only have 6 to memorize. That means everything else is a weak acid. So here they are. A lot of the halogens are weak acids, or sorry, strong acids. So HCl, HBr, and HI are all strong acids. So note here, what's not on this list is HF. See how if we look at the group 7, like FClBrI, fluorine is not a strong acid, but the rest of the halogens are. That's what I like to memorize, okay? That in group 7, when you have a hydrogen attached to it, HF is a weak acid, but the rest are strong. Then the other trends here are just some polyatomic anions with hydrogens attached to them. So I like to memorize sulfuric acid and nitric acid, because those are the ones you use the most in lab. So nitric acid comes from nitrate, sulfuric acid comes from sulfate, so see where they are on the periodic table, and then also perchloric acid, so a chlorate anion, or sorry, a perchlorate anion within there. So we have chlorine attached to 4 oxygens, and then also, oh wait, that's it? Yes, that's it, okay, so you don't do phosphoric acid. Okay, yeah, so those ideas. So I just memorized that the polyatomics associated with nitrogen, sulfur, and chlorine are also strong acids within there. Do note the number of oxygens in those polyatomics. Those are important. So the idea of our strong acids, these are our 6 strong acids. The reason they're strong is because they are strong electrolytes. Do we remember what a strong electrolyte is from chapter last one? Strong electrolytes, when you put them in water, they dissolve into all ions. That we don't have a equilibrium arrow. So note here. So here, ammonia is a weak base. See how there's an equilibrium arrow? It's weak. That means both sides of the equation exist at the same time. We have ions and some neutral molecules in solution. But when you put a strong acid in solution, like HCl, see how it's a full forward arrow. That means we have no HCl actually attached to one another in solution. It all exists as H plus and Cl minus in solution. So these are strong acids because when we put them in water, they fully dissociate into H plus and their counter anion in that case. So those are all our strong acids. So all of those will do that. They will break up into H plus and their counter anion. Our strong bases, I already mentioned, are our group 1 and 2A metal hydroxides. So group 1A, something like NaOH or lithium OH, so lithium hydroxide. That's group 1A, or something in group 2A, so like calcium hydroxide. 2A metals form what charge? 2A metals will form what charge cation? 2 plus. So how many hydroxides do I need? 2. Yeah, so it's CaOH, 2 of them, in order for it to be balanced in that case. Or something like magnesium hydroxide, same idea. Right, because it's Mg2 plus. So that's how you memorize the strong bases, that they're just hydroxide, so that's the giveaway. and they're attached to a metal, a 1A or 2A metal. And so that list is not complete for strong bases. All right. So if we know how to identify our strong acids, strong bases, then that means everything else is a weak acid or weak base. So let's look at those. So again, I want to remind you that the reason we call them weak is because they're weak electrolytes, both weak acids and weak bases. They're weak electrolytes, meaning when you put them in solution, you need the equilibrium arrow. Both sides of the reaction exist at the same time. You don't have as many ions in the solution as you would a strong acid or strong base. So that's the idea here, equilibrium arrow. You have neutral molecules and ions in solution at the same time. And basically how we memorize the weak acids, if it's an acid and it's not one of our 6, it's gonna be weak. Our weak bases, a common weak base we run into is ammonia. All right. I will point out that amine functional groups, they look like ammonia, right? Are also weak bases. Also, one more, and I think it's in the slides as well, carboxylate. Carboxylate functional groups are also weak bases. And that on the flip side, carboxylic acid functional groups are, what do you think they are? Are they strong acids? They are weak acids. They're acids nonetheless. That's why we call them carboxylic acids. And the idea is if you look at the functional group of a carboxylic acid, there's this, OH group hanging off that carbonyl carbon. That hydrogen on the OH is actually pretty acidic in that example. All right, and actually that's what acetic acid looks like. Acetic acid is a carboxylic acid, so CH3. So if we want to identify which proton will probably be donated in acetic acid, that's what this is. This hydrogen is typically donated. And so when we rip off that proton, we make a carboxylate. And in that example, carboxylate would be acting as a base. We could identify as a base, a weak base specifically. Okay. I think I already said most of this stuff already. We know our strong bases, they have to be 1A or 2A metal hydroxides, but just to kind of emphasize the difference between strong and weak bases are based upon our idea of electrolytes. So a strong base, when we put something like calcium hydroxide in water, it will dissociate into all its ions. So when we think about that, when calcium hydroxide aqueous, how it actually looks like in solution, we will see a calcium 2+ cation, but what else will we see in solution based upon its chemical formula? A hydroxide, but specifically we'll actually see 2 of them because there's 2, a subscript 2 in the chemical formula within there, right? So this whole idea, when we put 1 unit of calcium hydroxide in solution, we actually get 3 ions out. So calcium hydroxide will actually conduct a lot of electricity compared to the same concentration of a weak base, so such as ammonia or something. Because when we draw ammonia, and I think we already wrote out the equation for the base nature of ammonia. So you take ammonia, you add it to water. Ammonia is a base, so it will not donate a proton, but it will accept a proton. So when you accept a proton, you're taking it from water. So the product here is NH4 plus and OH minus. So when we look at this, the ions that are present are the NH4, the ammonium, and the hydroxide. So there's ions there. But this is a reversible reaction, so both sides exist at the same time. So we don't actually get 2 equivalents of ions here when we dissolve ammonia. We get something less than 2 equivalents of ions versus in calcium hydroxide, we get the full-blown 3 different ions when we dissolve calcium hydroxide in water. So that's the big idea. And I really want to emphasize the type of arrow that is used because that will give it away, right? If I give you a chemical equation and there's a double arrow in it, you can immediately say, oh, that's a weak something, so a weak electrolyte in a sense, because all weak electrolytes will have those double arrows, right? Don't want to make it, so that's like a cheat. It's like a hint or cheat on the exam, okay? Because I'm very deliberate about what arrow I use. I don't just use any arrow I want. Okay. All right, so there are our strong and weak, so same definitions as previous. So let's not spend too much time into naming acids. I do want you to recognize that how we name acids actually stems from our naming from chapter 3 that we did at the beginning of the year. All right, so note here when we think about an acid, like the acids we've been looking at, do you see how they kind of resemble ionic compounds? Because hydrogen, it's H+, and it's associated with an anion. So that whole idea of identifying the cation in an anion will help you a lot in naming acids. So when you name an acid, identify what anion it is attached to, specifically the name. Because whatever the name of the anion is will tell you how to name the acid. So here are the rules. If the anion ends in the ending "ide," like if that anion was just in like a regular like sodium, like ionic salt, like sodium blah, whatever that name is, if it ends in "ide," your acid name turns into hydro, and then the name of the anion, but you replace "ide" with "ic," and you name it acid. I know that sounds like a lot, but I just like to memorize that HCl is hydrochloric acid. And that helps me because I know that Cl- is what anion name. It's chloride. So like NaCl is sodium chloride. But when it's not Na, when it's hydrogen instead, you take the chloride name and you add hydroic acid. So it becomes hydrochloric acid, right? Yeah, so my example here. So here, HI. HI. What is the anion in HI? Iodide. But when we name like a salt, an ionic salt, do we call it iodine? What do we call it? Like NaI, when we name that. It's not iodine, it's iodide. Yes. So it's iodide. Again, I always start with what is the iodide. Okay. What is the anion? And then you do the rules here. Since it's ide, you do hydro, name, ic acid. So hydro, iodic acid. That's the name. So note how that looks. HI looks like HCl. And the name is similar. Hydrochloric acid, hydroiodic acid. So I will point out that this one, the first one that I showed you, it's the most complicated one, right? It's the next ones that are a little bit easier. When we have acids that are attached to polyatomics, they're much easier. So the next one, it's if your anion ends in 8, like a lot of different polyatomic anions we've run into. Sulfate, nitrate, what else? Phosphate, carbonate, acetate. All of those 8 endings, when instead of like a metal cation, when it's a H+ cation instead, you just change the 8 ending to ic acid. So that's nitric acid. Nitric acid has what anion attached to it? Nitrate, right? How about sulfuric acid has sulfate as the anion. Phosphoric acid has phosphate attached to it. So I think that one's a lot easier. All right, so do we have one? Yeah, so H2SO4, right? If this was Na2SO4, that would be sodium sulfate, right? SO4 is sulfate. So again, I like to identify the polyatomic sulfate. And our naming rules here, if it ends in 8, it just comes ic acid. So this would become it's not sulfic acid, it's sulfuric acid, so they add an extra UR for sulfur. So it becomes sulfuric acid in that case, all right? So how I like to memorize these kind of is that the more complex the anion, so like for example, sulfate versus the previous one, just HI, like sulfate, H2SO4, that's a much longer complex formula, right? The polyatomics acids have the simplest names. They have the simplest names versus something like a simple chemical formula like HI, HCl, HBr. They have the longest names. That's how I memorize it, right? If you look at like HI, it's hydroiodic acid, like bunch of syllables there. But something like HNO3 would just be nitric acid, though it has a long chemical name. So that's how I memorize it. Oh my gosh. Sorry, guys. Did we get the internet back yet? What? Not yet? Okay, so there we go. So that's I'd, we did the 8, now the ite. So some of our polyatomics we ran into, when they had one less oxygen, instead of sulfate, it would become sulfite. Or nitrate would become nitrite when there was one less oxygen. That was the common trend that we saw there. So when you have an ite ending, it just becomes OUS, us acid. And so that's the trend within there. So it's the same exact thing within there. Because if we look at the example here, SO4, that's sulfate. So SO3 would be sulfite. Sulfite, if we were doing naming like we did from chapter 2 and 3. So that means ite, the ending is ite, so then our acid name becomes sulfurous acid. Us. Versus eights become ix. Ites become us. So let's work a little bit backwards here. What about this one? So phosphoric acid. So work backwards. Identify the acid ending. Then identify what polyatomic anion is attached there. So phosphoric acid, what polyatomic is shown there? Phosphate, yes. So my strategy here, we want to write the chemical formula. All right, so you identified ic acid, it's phosphate because it's ic acid. So then you ask yourself, what is the chemical formula of phosphate? So that's something you do have to memorize. So phosphate is PO4, do we remember the charge? It's 3 minus, all right? So PO4, 3 minus. So that's phosphate, but is that an acid? Is phosphate an acid? No, we have to add H's to it. But now the question is, how many H's? 3 of them, yes. So it's H3PO4. That is the chemical formula for phosphoric acid. You see that? What would phosphorus acid be? Would phosphorus acid be? H3PO, 3 of them, yes, because us acid is ite, so it's phosphite. So that means that the phosphate just loses 1 oxygen. So it'd be H3PO3, yes. All right, so that's how we name. So this is all contingent that you know how to name like ionic compounds. So do bring that out of the vault. You have to use it in a couple weeks anyway when we have the final, because I think, there's like 28 days left? 28 days left. Don't say that. Okay. It makes me excited. All right. So we said that acids and bases, they're like the yin and yang of chemistry here, of the solution chemistry. They're opposites of one another. So what's nice, oh my gosh. It'll kick up, is it working? Is it? No, but my thing, look, there's no, oh, you can't even see it. Okay. Is it, you're not playing? Is it working? I saw a bunch of people leave. Do you think so? What's wrong? I don't care. I don't care. I don't care about Zoom people. They knew. Yeah. Okay. I'm gonna. What am I doing? Did I log out? Oh, cool. Oh, cool. Okay, they can just watch the recording, right? Right? They'll just watch the recording. Okay, there we go. All right, because that records on here. It records on there. All right. Okay, so I'm just going to keep going. Wow, it's so much bigger when I don't zoom. Is that bigger? Wow. Okay, so acids and bases, opposites of one another. So when we react to them, an acid and a base, something special happens. We call this a neutralization reaction, when an acid and a base react with one another. The special thing about acid-base reactions is regardless of what the acid is and what the base is, the products will always be water plus a salt. It doesn't matter if it's a weak acid, weak base, or a strong acid, strong base, or any combination of those. It will always be water and a salt. Because if we remember acids, H plus associated with it, right? Bases have OH associated with it. So what's H plus OH minus? It's HOH, or water, right? So when we react an acid and base, we always get water, and then the other thing we get is a salt in that case. So in this reaction, we are reacting HCl, sodium hydroxide, so we have our acid and our base, and really this works like any double displacement reaction we've done before. So we have H combining, so our H plus combining with OH minus, we have Cl minus combining with Na plus within there, and so we just swap our partners. So you can clearly see that one of the products we make is H2O, because it's H plus and OH minus. What's the state of H2O? Liquid. In this case, it's a liquid, yes. And then what's the other combination when we switch our cation-anion partners? What is it? NaCl, yes. So our other product is NaCl. And now, what do we think what the state of NaCl is? Think about this. So HCl is a liquid, or sorry, aqueous, it's a solution. Sodium hydroxide, also a solution. When we mix those two together, we get water and a salt, in this case, sodium chloride. What do we think the physical state of NaCl is? Yeah, I knew you would say that, but it's not a solid. It's not a solid, because all of this is happening in what? Water. Does salt dissolve in water? Yes, so that means salt is actually not solid, but it's aqueous. See, I got you there. Yeah, so it's aqueous in this case. All right, so there's our neutralization reaction. See, acid plus base gives you water and a salt. And just replace the acid with any acid, or any base with any base, and you will get the same thing. The whole idea here, this next line, net ionic equation, if we think about which of these substances are strong electrolytes, HCl is a strong electrolyte, sodium hydroxide is a strong electrolyte, sodium chloride is also a strong electrolyte. So really the true reaction that's happening right now is H plus is combining with OH minus to give you H2O, liquid in this case. Because really that chloride and that sodium, those chloride and sodium ions, they're really not participating in the reaction at all. They're not really changing on either side of the reaction, because they're tied up in strong electrolytes on one side, tied up on strong electrolytes on the other side. The only thing that's really changing here is that we're combining a H plus and OH minus, and that we're making it one thing. In this case, it's water. So this is the net ionic equation. And this is true for many acid-base neutralization reactions, that the main thing, the important thing that's happening is this reaction right here. All right, so neutralization reactions, that's like the really sterile, like chemistry definition of a neutralization reaction. If we think about neutralization in terms of what we do, how we use the idea of neutralization within our bodies, when we think of antacids, if we've had too many margaritas and your stomach starts to turn and you want to figure out how to fix it because, I don't know, you have like a date to go to or something, but you have an upset stomach and you want to figure out how do I fix it, right? Then you take antacids, but not all antacids are equal. When you think about taking an antacid for an upset stomach, there's lots of options out there, right? Really, well, for me, it depends on whatever I have on hand, like that's what I'll use. But if you were at the store and you had the choice of choosing an antacid, there's like a huge selection, all right? So here are just some examples of antacids, so let's go through them. There is, the first one is milk of magnesia. I doubt many of you have actually taken this. I feel like old people do. Well, no, milk of magnesia, I don't know. I just feel like old people take it. Like you'll find it in their cabinets. Okay, yeah? Okay, exactly, you've never heard of it. But if you ask your grandparents, maybe they've probably heard of it. Okay, yeah. All right, the more common things, Tums, right? Tums is an antacid. I would probably take Tums if I had too many margaritas. Or Pepto-Bismol, right? That's actually another antacid. It's more expensive than Tums, but to me, I actually like Pepto-Bismol more. And there's a reason for it. Because if we think all of these things neutralize acids, because our stomachs are acidic. When we have an upset stomach or a sour stomach, really what that means is you have an imbalance of H+ in your stomach. All right, and then it's causing some issues. So when we take an antacid, what we're essentially doing is neutralizing the excess acid in our stomach. But remember, we're neutralizing the acid, so we think about the net ionic equation. We're neutralizing it, right? We're taking some medicine to neutralize the excess H+ in our stomach, and it makes water. That's like benign. But we can't forget that there's other things happening as well. They're there. So something like, remember in our HCl, NaOH example, there's NaCl floating around in solution too. So when we look at these examples, there's other things in solution, not just the H+ and the OH. There's other things that can cause for some discomfort. The question here?
Yeah, so like, I was also told outside of like Pepto and Tums, just drink regular white milk to help with that. So in cases like it has help if I just drink 2%, I'll be fine, or even bread.
See, okay, so that's a different mechanism. So the question is that a treatment for an upset stomach would be drinking milk or eating bread. So that's a different mechanism. This is like straight up, we're neutralizing the acid. So milk, a lot of people think milk is basic. I don't know why, but it's actually acidic. Milk is acidic. The reason I think they're having you take milk is because there's fat in it, and the fat will line your stomach so it doesn't, the excess acid doesn't irritate it. That's what I'm thinking. Or bread. Bread will just soak up the acid. So yeah, it's not reacting with the lining of your stomach, and that's what's causing the discomfort. So I'm not a doctor, or that kind of doctor, okay? But that's what I think, okay? Yeah. I don't see that, I mean, you're taking milk or bread, like that's not gonna hurt you. Okay. All right, so the idea of these antacids, the idea they all neutralize excess HCl. Milk of magnesia, this first one, milk of magnesia just contains straight up like hydroxide. And it's attached to not a 1A or 2A metal. Usually milk of magnesia is a combination of aluminum hydroxide, where's that? Aluminum hydroxide and magnesium hydroxide, all right? So it's just straight up has hydroxide. So you see how that can neutralize stomach acid, right? Okay. Problem with milk of magnesia, all right, is that magnesium, extra magnesium, too much magnesium in your system causes diarrhea. Right, so not so great if you had too many margaritas and you're on a date. Not so great, okay. But it neutralizes it, right? But again, you have to think about what else is there. In this case, the hydroxide is attached to Magnesium. Too much magnesium gives you diarrhea. That's not great. Okay, all right, let's look at the next option. All right, so Tums. Tums is actually calcium carbonate. Or I think it's sodium bicarbonate, but it doesn't matter. It has carbonate in it. Do you remember the Arrhenius equation, how he identified acids? It was an acid when we added it to carbonate and it made bubbles. So when we take calcium carbonate, Tums, all right, it's that carbonate is neutralizing our stomach acid, but it's also making what? Gas, in this case CO2. So is that great during a date if you have too much gas, if you're producing gas in your stomach? No, that's not great. Especially, I mean, it's great that you're neutralizing the acid, but the byproduct here is a gas, and that can cause for some discomfort as well. So it's not good to take a lot of Tums in one day for a couple reasons. One, you'll get really gassy. Two, too much calcium in your bloodstream, also really bad. All right, so don't take too many Tums. But like, 1 or 2 or whatever, it's not a big deal. All right, so the last one is Pepto-Bismol. All right, this stuff's expensive. It's really expensive. Like Tums, this jar, like you get off-brand, it's like $2 for a thing, but like Pepto, it's probably like $9 for that little bottle. All right, so this is the structure of Pepto-Bismol. Do you see how it looks like a base? Do you see how it looks like a base? Right? Bases are characterized by what group? OH. Do you see the OH? It's right there. All right? So that's the active ingredient in Pepto-Bismol. So when you take Pepto, that OH goes and finds other H pluses, neutralizes it. That's great. So the other part that's there, that big bismuth molecule, it really does nothing in your system. So really, me personally, as I get older and I become like more sensitive to things, I go for Pepto-Bismol. Though it's expensive, it causes the least discomfort in my pains. And the reasoning is because it, one, neutralizes the acid, which is what, the extra acid in my stomach, which is what I want, but it doesn't cause other discomforts like, too much gas because of the CO2 produced when you take Tums, or giving me diarrhea like magnesium would. That's why I go with Pepto, all right? So that's just me. All right, we see all that? See, so much valuable and valuable chemistry in our everyday lives. All right, so let's just, wow, we're only on slide 15. I'm going so slow. All right, so let's keep going. Chemical equilibria. We've already seen double arrows before. Remember, in chemical reactions, double arrows just mean reversible reactions, that both sides of the equation exist at the same time. So when we think about chemical equilibria with reversible reactions, chemical equilibria or equilibrium in a chemical reaction is achieved when the rates of the forward and backwards reaction are the same. This is like a common misconception when we talked about it in the previous chapters. When a reaction is at equilibrium, it doesn't mean that the concentrations are equal. It means that the rates are equal, going forward and backwards. So that's the big misconception. Not that the concentrations are equal, but the rates are equal. So if the rates are equal, what we observe is that the concentrations don't change over time once a reaction is at equilibrium, right? So that's the big thing. And then the question is, how do you recognize chemical equilibrium? There's a double arrow, a double reaction arrow. And this is related to a lot of the things we've talked about before. Weak acids and weak bases have these equilibrium arrows, all right? I think it was from chapter 3, I don't know. Okay, so a little bit more detail into reversible reactions. So I've told you that when you were at equilibrium for a reversible reaction, concentrations don't change. So how chemists kind of quantify this is we can calculate the equilibrium constant for a chemical reaction. So what it really is, the equilibrium constant, or K, capital K, is the ratio of the concentrations of products and reactants at equilibrium. So the basic form of our K expression is you look at the chemical reaction, you multiply all of the concentrations of the products on the top, and you divide the product of all of the reactants on the bottom. Do note that we have to take into account if there are coefficients in front of them, in front of the substances, you need to take into account of them. I think when I show it this way, it's much confusing. It's very confusing because it's not real substances. If I show you an example, you can put together a K expression very easily within there. The important thing is that your K equilibrium constant has to take into account concentrations. So we can only put in substances that have concentrations. So in practice, what that means, it's things that are AQ, aqueous, or a gas. Do I have a gas in here? No, I don't. Or a gas. Anything that's aqueous or gas goes into the K expression. If it's a solid or a liquid, it does not, because those substances typically don't have concentrations associated with them. So if you look at this equation, you see substance E. Do you see E? Like E, it's a product, right? It would go on the numerator part of the K expression, but do you see it in the K expression? No, you don't, and that's because it's a solid. But you do see C and D in that case, right? And so note here, you see that like for C and D, the coefficients are become the exponents within your K expression, right? And so what goes into this K expression, C, D, A, and B, those are the concentrations of those particular substances at equilibrium. All right, so let's so let me show you this example. So here's another a real chemical equation, right? So if we wanted to write the K expression for this reaction, I just like to remember it's products over reactants, right? So you take the products. What's the product? What's the product in this reaction? HI. So you do concentration of HI. I use the brackets. But then you look at the coefficient. How many? Yeah, there's 2 of them. So the 2 becomes a exponent right there. All right, so that's my numerator. Then my denominator, so those are all the products. So now we do the reactants. The reactants are H2, so we do concentration of H2. All right, there's just a 1 coefficient, so you don't need an exponent. And then you do times the concentration of I2, iodine. Okay. You see that? So that's the K expression. And it's right here. I know it's right here, but like I want you to build it. All right. So products over reactants, don't forget the coefficients become exponents. That's my definition of K. So what this table is trying to show you is that at equilibrium, the concentrations of all the products and the reactants given the K expression will always be the same number, right? So what this chart's trying to show you is if I put the reactants in a vessel, so like 1 molarity of each. If I put 1 molarity H2, 1 molarity I2 in the reaction vessel, the reaction will go forward, and then it will, then the concentration at a certain point will stop changing. Right, that's where the rates are equal to one another, equilibrium has been achieved. So if you actually calculate the concentrations of everything at equilibrium and plug it into the equation, you get this number, 51.5. Okay, great. But then if you change the concentrations of things at the initial, initial part of the reaction. So in this case, experiment number 2, we don't put the reactants in the vessel, we just put HI in the vessel, so just the product. So if we do that and we close up the container and let it go, the reaction will go in reverse. Try to make up some of the reactants. The concentrations will change, but then at a certain point they'll stop changing. Equilibrium has been reached. So at that point, if you calculate all the concentrations of everything, plug it into the equation, you'll get the same exact number, 51.5. So that's the whole idea, that you can start with any amounts of whatever. The reaction will change itself because it's a reversible reaction, so it can achieve that equilibrium constant. That's the whole idea within there. So that's what this is. In this case, 51.5 is the K value, the equilibrium constant for the specific reaction at this specific temperature. All right, so there we go. So looking at the value of K. So here's our K value. 51.5 is our number. If we kind of look at the K expression for this reaction, 51.5, what substance at equilibrium is the most abundant, is the most concentrated? You have all the concentrations of everything there, right, in all the experiments. Which substance is the most abundant? The product, yeah. But let's think about it mathematically. So yeah, if you look at experiments 1 through 4 and compare the numbers, see how HI is like the largest amount in all of them? But let's just look at the K expression. If K is a big number, is the numerator large or is the denominator large? The numerator. The numerator is the concentration of the products. So that means there's a lot of products. Versus a very small K value. We have a small K value, what's big? What's the big number? The numerator or the denominator? Denominator. So in that case, if K is small, which side of the reaction is more abundant? The reactants, because it's the denominator, right? And I think that's what the next slide says. So really, it's just kind of applying the idea of the mathematics. So if you recall what the general form of K is, it's products over reactants. So if K is large, your numerator is big. So you have a lot of products. If K is small, you have a very large denominator. So you have a lot of reactants in that case. So that's a way that you can kind of just qualitatively gauge, what substance is most abundant when given a K value, right? You can tell a little bit about the reaction. Like if it's a really big number, you can say, ooh, yeah, the products are really favored in that reaction, right? Okay. And yeah, just based upon mathematics there. All right. Okay, so let's actually do a problem here. All right. So really when being asked about K values and all that, really the first step is start with a balanced chemical equation. Because once you have the balanced chemical equation, you can write the K expression. I have to give you some data in order for you to solve problems that involve K expressions. I have to give you concentrations. So in this case, I give you the balanced chemical reaction, and I tell you the K value. And I say, okay, here's the concentration of one of the things. What's the concentration of the other thing at equilibrium? So my idea here, my strategy is, okay, start with the balanced chemical equation. We have that. And then write out the K expression. Write out the K expression, and then plug in everything we know, and then solve for what we don't know. All right, so let's do that. So given this reaction, here's the K value. So let's write that K expression. So K is products over reactants. So what substance goes in the numerator? NO2. Just one NO2? Two of them. So yeah, superscript 2 of them. Note how I didn't put like a 2 in it. All right, I didn't put the 2 in the parenthesis. I did it as a superscript. All right, so there's only one product, there's only one reactant. So the denominator here is N2O4. Any exponent? No. Okay. All right, so that's the K expression. We have the value of this, right? It gives it to us. This is equal to 0.211 at equilibrium. Right, and so the other piece of information that's given is the concentration of N2O4. So that means we have the value that is the denominator, right? We have that number. So at this point, you see, we just plugged in 2 numbers, we have one unknown. So we just solve for the missing piece at this point. Because the question is asking what's the concentration of NO2 at equilibrium? So at this point, yeah, we just calculate the numerator. So I'll just rewrite it. I'll just call it x. So x squared over 0.00452 equals 0.211. Oh, did I forget my calculator? No, I have a crappy one. All right, so 0.211 times 0.00452. 452. So I'll rewrite that as x squared equals 0.0009 0.953, and then just take the square root of both sides. Oh no. Oh no, how do I do square root? Okay, I got 0.03, how many sig? I'll do 3. 0.0309 molarity is the answer. And so I always like to associate that number of what it is. That concentration is the concentration of what? NO2, yeah, that's what I assigned as X. So NO2. And a way to check yourself is put that number back into the K expression with the other number we know and see if you get K out, the same K out. That's a way to just check yourself within your math there, right? And so see how else I can ask equilibrium questions like this. I can give you the expression, I can give you the concentrations of everything and have you calculate K. So that's another way I can ask questions like that. Or I can give you K, all the concentrations but one, and then you calculate for that missing concentration. Right? So that's kind of the way I could ask questions on an exam. Okay, easy enough? Okay, yeah, question.
What if an acid or base, the higher the K, the stronger the heat, right?
Yes, yeah, it is. So we'll get there. The higher the K value for an acid, a weak acid equilibrium, means that the reaction goes forward a lot, that the products are favored. And so we call that a strong weak acid. And it's like in the next coming slides, I think. All right, okay, we don't have enough time to do stuff, but I'll just kind of give you a preview of what's to come. So that's the mathematical part that we can talk about chemical equilibrium. We can also do some predicting of ways that chemical reactions can shift based upon if we make small changes. Remember, reactions are always trying to achieve equilibrium. Right? So if you poke the reaction and do a little bit of change to it, the reaction will adjust itself so it can go back to equilibrium. So keep remembering that reactions always want to go back to equilibrium conditions. So that's why I have a seesaw here, all right? So if you think about equilibrium as like where the seesaw's balanced, if you make a change in one direction, the reaction's going to adjust itself so it goes back to equilibrium. So this chart kind of summarizes the way that reactions can shift, either left or right, but really I think it's best to just look at the reaction itself, all right? Yeah, so basically this is called Le Chatelier's principle. If we make small adjustments, changes to a reaction, how is it going to adjust itself? So this is another way to think about it. If we add more reactant, the reaction's going to push itself to the product. So I like to think of it as a seesaw, right? So if you add more reactant, the reaction has to shift what way to become balanced? It has to shift in the forward direction in order for it to be balanced. Or if you think, okay, what if I remove H2 from the reaction, right? Then the seesaw kind of goes like this. So that means which way will the reaction go if I remove H2 of reactant from the equation? Yeah, it goes this way, right? So basically how we think about it intuitively works better than just memorizing that chart, all right? And we'll look into more examples on Thursday, all right? So there's a little preview to Le Chatelier's.